Okay, I want to talk to you about why is this topic actually important. You might recognize this from your fertilizer when we briefly talked about fertilizers. Why is this topic important? This topic is important because of industrial chemical processes. Many of the things that we want to do in industry are based on reversible reactions, and obviously the goal is to make money in industry. So if you've got a reaction that's reversible, it's not actually helpful because you want a lot of products. So you want only products to be formed. And one of the main places where these equilibrium reactions are occurring is in the fertilizer industry. So this topic keeps popping up now with the equilibrium thing with fertilizers, and then there's another one with electrolysis. Part of this comes up later on when we do the other topic. So first of all, I want you to think of industry. So we sometimes think of our science as being those tiny little test tubes and beakers and everything. And temperature and pressure we don't have too much concept of because we're only used to the air pressure where we live, which is 1 atmosphere. So if you have a look here, this isn't your average fertilizer factory, and you can see there's a million miles of tubes and these heavy containers and everything. And these are all actually to deal with intense heat and intense pressure. And so this is what we look at when we look at an equilibrium in industrial chemical processes. And you have to realize here we start talking about moderate temperatures. Moderate temperatures are not a temperature at which you can live in the chemical industry. They're moderate in terms of how much energy does it take to do something. So for instance, if you think about making steel, you need really thousands of degrees centigrade to make that work, or degrees Celsius to make it work. So one of the main things we're going to do here is look at these things in the fertilizer industry. So there's a lot of overlap with this topic. This topic overlaps with reaction rate because of catalyst. It overlaps with fertilizers because of the chemical reactions. So this topic kind of doesn't have a home, and we learn about it's in bits and pieces all over the place, which is very infuriating for me. So let's have a look here, but bear in mind this is what an industrial chemical process is going to look like. So equilibrium in industrial chemical processes, most of the things that we make money from actually are very, very slow reactions, and they need to be done under high pressure. But if you want to make a high pressure system, you need really, really strong metal containers, and if they explode, people die. So it's really hard to build, and you don't actually want the high pressure because of the danger. So you have to weigh everything up. How much yield am I going to get? How many products is my reaction going to produce versus how much did it cost me to make them? How much did it cost me to make the container? How much did my chemicals cost? How safe is it? Things like that. Okay, so we're going to have a look at two reactions, the Haber process and the contact process in terms of this. So the first one is the Haber process, and remember I showed you all of those people picking up bird poop to fertilize the lawn. So this is the process, and the bat poop as well. This is the process that replaced us having to go farm bird poop and bat poop, because it started making ammonium products that give nitrogen, like to get your lawn to go green and to make your mealies to grow fast and tall and green as well. Okay, so it's the production, the Haber process is the production of ammonia, which we use for fertilizer and for cleaning agents like Handy Andy. So if you see here, it's a reversible reaction. Nitrogen plus 3 hydrogen goes to 2 ammonia, and it is exothermic over here, as you can see, because it's got a delta H that's negative. So what we have to do is, this is slow, this reaction is really, really slow. We have to look at two things, the reaction rate and the yield. We want this to happen fast, and we want a lot of ammonia, the product. So how can we do this? To increase reaction rate, we know how to increase reaction rate. We must use a positive catalyst. Okay, remember the catalyst lowers the activation energy, and both the forward and backward reactions go faster because that's the job of a catalyst. The other thing we can do is, we know that reaction rate depends on enough particles having activation energy for successful collisions. So for any reaction, if you increase the temperature, you increase the reaction rate because you have more particles with activation energy or more. Okay? And if you increase the pressure of the system, that's also like increasing the concentration of the reactants. Remember, reaction rate depends on temperature and concentration. So if you increase the pressure, you're increasing the concentration. And as well, if you want to increase the reaction rate, you have a high concentration of nitrogen and hydrogen, which overlaps with increasing the pressure of the system. Okay, so these are all reaction rate now. But if you look at this reaction over here is exothermic. Okay, so in terms of Le Chatelier's principle, increasing the reactant concentration, perfect, that's the nitrogen and hydrogen, it'll drive the equilibrium to the right, we get more ammonia. So that's a good thing for yield. But the forward reaction is exothermic. The moment we increase the temperature, we actually want to drive the equilibrium backwards. So you have to strike a balance between increasing the temperature to increase reaction rate and decreasing the temperature to favor the forward reaction, because the forward reaction is exothermic, so you need to decrease the temperature to favor it. As well, you need to increase the pressure so that the yield is favored. Okay, so previously for reaction rate, increasing the pressure was for increasing the reaction rate, because it's like increasing the concentration, you're going to get more collisions. But over here, if you look, 1 mole, 3 moles, so 4 moles of reactants go to 2 moles of products. So the moment you increase the pressure, the system tries to, according to Le Chatelier, decrease the pressure, it drives the equilibrium to the right. So increasing the pressure not only increases the concentration and favors successful collisions, it also favors the forward reaction, which produces less moles of gas. And then the final thing you can do to increase ammonia yield is take this ammonia out of the reaction container, because remember, if you lower the concentration of the products, the equilibrium is going to shift to the right to replace them, also according to Le Chatelier. So you have to strike the balance, especially with this temperature thing, because you need to increase the temperature to increase reaction rate, but you need to decrease the temperature to increase the yield, to shift the equilibrium to the right. So what you have to do is we use what we call in physics, or well, in industry, a moderate temperature. So the moderate temperature lets the reaction proceed fast enough, but it doesn't decrease the yield. So now these are optimal conditions for the Haber process. You have to learn them, I'm sorry to tell you. So I don't know what you're supposed to do to learn them. You've got to figure out some way to do it. But the temperature is about 450 degrees C. You see why I say this word moderate is only the use of moderate in terms of chemical industry, not in terms of what we would like, because obviously we like the moderate temperature of 25 degrees. Then as well, a pressure of about 200 atmospheres. So that's 200 times the pressure at the surface of the Earth on the average day, which is pretty darn high, but it's actually not that high for industry. And then you need a catalyst. They use iron or iron 2 oxide. Notice this is iron oxide, but it's iron 2, not iron 3. So these two catalysts are quite cheap. Iron is cheap, iron oxide is cheap, so they better used. Sometimes I think you can catalyze this with platinum, but that's far too expensive and gets contaminated, so they use the iron or the iron oxide catalyst. Okay, so how do we start the Haber process? How do we get the reactants? We get the reactants through a couple of means. So I need you to cast your minds back to grade 10 over here, to distillation. Like for instance, if you mix alcohol and water and you want to separate the alcohol out from the water, you would use this distillation apparatus, because alcohol and water have 2 different boiling points. So distillation separates things with different boiling points. Basically, you heat something up, and the thing with the lower boiling point becomes a gas first, okay? And then it rises up out of the liquid, and then you cool it. You collect it in a pipe, and this pipe's got cold water flowing around it, and then it cools back down into a liquid and comes out the other end. So this is the distillation we learn in grade 10 to separate, for instance, alcohol and water. But now for the Haber process, we want nitrogen. So remember, the air is like 80%, almost 80% nitrogen. So we distill nitrogen from the air, okay? Because in the air is nitrogen and oxygen. So nitrogen gas, if you look here, it's got a boiling point of minus 190, and oxygen has a boiling point of minus 185. So what you do is you have a massive thing that looks like this, okay, but this is how the process works. So what happens is you suck some air into a container at the beginning here, and then with somehow this is a piston, you compress the air. Now remember the gas laws. If you compress a gas, it'll heat up, okay? Remember PV equals nRT, so you get the gas in here, the air from the air. You squash it so it heats up, and then obviously if you're heating something up, then it gets more energetic, and then they force it into this other container, and this container's got liquid nitrogen in it, which cools it very rapidly. Okay, so they cool this air that they've just squashed, and then the compressed air goes through another pipe into another chamber, and then after it's been compressed, it's allowed to expand again. And remember, this also causes temperature changes. Compression and expansion causes temperature changes. And what happens then is that it eventually turns into liquid as a result of all the squashing and cooling and all the rest of it. And it goes into another vessel, and at the top here the nitrogen gas comes off, and at the bottom the oxygen comes off, because they've got different boiling points. So it's a little bit tricky to understand, but it's not that important. You just need to know we get nitrogen from the air by fractional distillation. Okay, remember we also talked about distillation of oils. When you get crude oil out, we had a distillation column when you crack. Remember, when you crack, there's a distillation column with that when you get out the different weights of alkanes and alkenes out of the fractionation column. Okay, so we get the nitrogen from the air by fractional distillation, and we use methane to make hydrogen gas. So this is a little bit more complicated. You don't need to know all of this nonsense. You just need to know that they get methane from hydrogen gas. You get methane, and steam gives you hydrogen and carbon monoxide, and you mix the carbon monoxide with steam again, and you get out hydrogen gas and carbon dioxide. So this is like with coal. They do something similar to this with coal in South Africa, because we don't have that much natural methane gas. Okay, so that's the steps for the Haber process. Then we come to the contact process. Now remember, you must remember, the Haber process makes ammonia, the contact process makes sulfuric acid. You have to remember these two titles. You have to remember the contact process belongs with sulfuric acid. So to make sulfuric acid, you have 3 steps. You prepare and you purify sulfur dioxide from sulfur and oxygen. Now sulfur dioxide is a very nasty compound. It's related to allergies and global warming and stuff like that, so you have to be a bit careful. But you mix sulfur and oxygen, and then there's the catalytic oxidation of sulfur dioxide to sulfur trioxide, and eventually you convert sulfur trioxide to sulfuric acid. So this is the very complicated thing in the fertilizer industry thing that we have to talk about with that weird word oleum. But for now, we're just going to have a look at this catalytic process and the reversible reaction step. Why do we need sulfuric acid? It's in all your car batteries. All of these car batteries, they used to be called a lead acid accumulator because they're full of acid. And then we use it to manufacture fertilizer. And it's used in a whole bunch of other things in industry, like to make paint and that. So it's a good industrial chemical. So when we look at this process, remember the first one was making sulfur dioxide, and the second step, which is the step we're interested in terms of chemical equilibrium, the second step converts sulfur dioxide to sulfur trioxide. So 2 sulfur dioxide plus oxygen goes reversibly to sulfur trioxide. You can see this is also an exothermic reaction. It's way more exothermic than the Haber process. So we're going to look at the same things again. How do you increase the reaction rate? You use a catalyst. How do you increase the reaction rate? You increase the temperature of the system to give the particles more particles activation energy. You increase the pressure of the system. So this is basically also increasing the concentration, and maintain a high reactant concentration. So as the sulfur dioxide and the oxygen gets used up, you put more in so that they're always at a high concentration, so that when they're being used up, you replace them. So this is the reaction rate. Now again, we're going to go and look at the yield. Okay, so if we want to increase the yield, we want to drive the equilibrium to the right. So obviously increasing the concentration of the reactants and decreasing the temperature of the reaction will favor the forward reaction. Remember, this is exothermic, so if you decrease the temperature, it gets driven to the right. You can increase the pressure on the system, because here, look over here, 2 moles, 3 moles of reactants. 3 moles of reactants play 2 moles of products. So increasing the pressure on the system will drive the equilibrium to the right, because there were fewer moles of gas on the right. And you can also continually remove sulfur trioxide from the system, because remember, once we lower the concentration of this, according to Le Chatelier, the equilibrium will shift to try and undo the change that we've done. So what are the optimal conditions for the contact process? You can see the temperature is very similar to the Haber process, about 450 degrees, but the pressure is way lower. The pressure is only 1 to 2 atmospheres versus the Haber process, which was 200 atmospheres. So you almost don't need a pressurized reaction vessel to do this, which is handy. And this one has this weirdly named catalyst, vanadium pentoxide. So sometimes they put vanadium and they put the little V in brackets here, vanadium V oxide instead of vanadium pentoxide, to show you it's vanadium with a 5 for the Roman numeral stock notation. So you need to remember this catalyst as well. You need to remember this pressure. But this reaction actually goes to equilibrium at a low pressure. The equilibrium is quite far to the right. It's got very high Kc. You'll get up to 98% yield at the low pressure. So that's handy. It doesn't need a serious container. And that is the end of this topic. But you will see, hopefully we can get more time to do fertilizers again, and then we're going to return to all of this contact and Haber process in a little bit more detail again. But for now, you can see we've got the catalyst issue in the reaction rates. We've got the reversible reaction issue here, looking at where the equilibrium lies, and then later we look at this with regards to making fertilizers.